so now we're going to look at section 9.1, basic combinatorics. So here's a big question. How do we count items without counting them individually? In other words, how do I count a set of numbers that's so large that it just takes too long to count? So mathematicians have come up with ways of doing this kind of thing. We've looked at how it all plays out. And so here's some simple examples to help you see how this is done. So how many ways can I arrange these three letters? Okay, and there's a couple ways that you can do this to make sure that you get all the different arrangements that are possible. We're going to use a tree diagram, which is a visual representation of a systematic counting. And so based off of that, we can then expand that out and then get rules and procedures to follow for many more letters. So basically here's how it lays out. I'll go ahead and show it to you at all. So your first, I got three letters. Pick the first letter. I can choose A, or I can choose B, or I can choose C. If I choose A is now gone. And so in my second choice, I either have B or C. And then when I choose that letter, then I only have one more choice left. And so that's why we have it the way it looks. So here's how I can use a tree diagram to show all the different arrangements of those three letters. And then you can see that we can count how many we have at the end. We have A, B, C, A, C, B, and we can count those out. And there are 6 different ways I can do this. I can also give you the list of all the different arrangements. And that list is what's called a sample space. It's a list of all the possible outcomes in an experiment. The experiment being, I want to arrange these 3 letters. So our goal here is to figure out how do I get 6 mathematically just by knowing I have 3 letters. How can I do that? Okay. And so that brings us to the fundamental counting principle. So mathematicians looked at this in many, many different ways, and they realized, hey, I have different events. Okay? The event here in this case is simply this. I had 3 letters to choose from. The first event is 3 choices. Once I make that choice, I only have 2 letters left. So the second event would be the second choice. And the third event would be the third choice, where there's only one possibility after that. So E sub 1, E sub 2 are 2 events. The first event occurs this many ways, M1 ways. The second event occurs this many ways. So the number of ways that the 2 events can occur is the product of the 2 number of ways. So in this example right here, if I laid it out, I had 3 choices for the first pick. Then I had 2 choices for the second pick. And then I only had 1 choice for the third pick. 3 times 2 times 1 gives me a total of 6 ways. So how many ways can I arrange 4 objects, or 5 objects, or n objects? So I want to put things in order. And so I'll just lay this out for you. 4 ways, 4 times 3 times 2 times 1, 24 ways. 5 ways, 5 times 4 times 3 times 2 times 1, 120. Well, this brings us into this thing called a factorial. N ways is n times n minus 1, 1 less than that, times n minus 2, all the way down to 1. And that is defined as n factorial. An exclamation point means factorial. Factorial. And it literally means whatever that number is, multiply all the integers from that number all the way down to 1. That's what that means. And we use this a lot in mathematics, especially in these counting processes. You're going to see that very clearly. Special note for factorials, 0 factorial is considered to be 1, and 1 factorial is 1. So those are 2 factorials you just need to memorize, and then all the rest follow this pattern right here. So factorial in set is a set or group of n objects. A permutation is an ordering of the objects in a set. So a permutation is putting things in order. Okay? So if I want to line up people at the door, if I have 6 people, then it would be 6 factorial. So if I have a group of 6, then there are 6 factorial permutations or ways I can line them up. So n factorial is the number of permutations of a group of n objects. Now, next question. What if the objects in the n set are not all distinguishable from one another? What if I have, in a classroom, what if I have identical twins or identical triplets and you cannot tell them apart? What do I do in a situation like that? Since I can't tell them apart, I can't see the list as being different. So how do I deal with that? Let's look at this then. Let's look at the 3 letters where I have 2 identical letters. How many ways can I arrange these? Well, to help us out, even though the 2 objects look the same, they are still different objects. We just can't tell them apart. So how many distinguishable orderings can be made? Well, to help us see this, I'm going to put little subscripts on these 2 objects so you can see that they are different. In the course of setting this up, we're going to go through the same process we just did. So here's the 6 ways I can line up 3 objects. Okay? But since I can't tell B1 and B2 apart, remove the subscripts and I get this right here. A, B, B, A, B, B. See? And I'm repeating things. I can't tell these 2 apart. So I don't count them as separate. I count them as one because it said distinguishable. I can't distinguish these 2 apart, so that only counts as 1. And so that's what we're doing here. So there's only 3 distinguishable permutations if I have repeats. So how do I do distinguishable permutations? Then a set contains n1 of one kind of object, n sub 2 of the second kind, and so forth and so on. And the number of objects is just the sum of all those. And then the number of distinguishable permutations is, there's that n factorial. And then I'm going to divide it by the number of each type that we have. Okay? Now I'll show you how this looks. How many distinguishable ways can I rearrange, can I order the letters of the word banana? How many ways can I do that? So I'm going to show you how this looks in an example right here. So the first thing I usually do is identify how many letters I have, how much of each letter I have. There is 1 B. There is 1, 2, 3 A's. And the letter N, there is 2. If I add these up, I get 6. And there are 6 letters in the word. That means this number of distinguishable permutations is 6 factorial. This letter, factorial, times the number of this letter, factorial, times the number of times n occurs. And so this formula then will tell me how many distinguishable permutations I have. And then you can use a calculator to help you out with this. Let's go find the factorial. I forgot where it was. Not there. I believe it's in this one. No, it's down here. So right down here on the calculator, there's a little button right here. That button has the factorial in it. And so I can use the fraction button. I can type 6. And then I push this button and do the factorial. And then come down here and I can do 1 factorial times, going to use the times button. 3 factorial times 2 factorial. And so once I have that in there, I can just hit enter or control enter, and I get the number 60. So this answer here is 60. Okay? If you need to do it by hand because you don't have a calculator, then just do as much of these as you can. For example, I can do 6 factorial, but see, the biggest one down here is 3 factorial. So 6 is 6 times 5 times 4 times 3 times 2 times 1. The 6 factorial has a 3 factorial in it. So 6 factorial is 6 times 5 times 4 times 3 factorial. 1 factorial is a 1. This 3 factorial right here, and 2 factorial is 2 times 1. These will drop out. This 2 and that 4 can reduce. Leave me a 2. 1 is all that's left on the bottom. 5 times 2 is 10. 10 times 6 is 60. So you can still do it by hand. All right. So now the next question is, what if I have n objects, but I only want to arrange a certain number of them at a time? I don't want the whole group. Okay. How do I do that? So if I have a group of, say, 15, but I only want to take 5, how many ways can I order up those 5 out of 15 people? That's what this is talking about. This is called a permutation of n objects taken r at a time. So here's the formula for it. NPR. There's the formula with the factorials. R is going to be less than n. If r is greater than n, then you have 0. In a classroom of 20 students, how many ways can we line up 5 students at the door? So I have the randomness of picking 5 students, and how many ways can I pick 5 students, and then how many ways can I line them up at the door? That's what this boils down to. Well, because I recognize this as an NPR, a permutation of n objects taken r at a time, because line up means order, permutations are putting things in order, that's a key thing to remember. This becomes NPR, which is 20 people taken 5 at a time. That's how you would write it. By formula, this is 20 factorial divided by n minus r factorial, which is 15. So this is 20 factorial divided by 15 factorial. And then we can work this out, because then you'll notice it gives you kind of an alternative way to look at this problem. There's 2 ways to look at this. One is this way, and I'm going to show you on the calculator how to get it directly. But because of the nature of this, I had to take 5 people at random. So this right here is going to be 20, 19, 18, 17, 16, because this is 15 factorial, and then these will drop out. So I'm left with just that right there. And if you think about it, that makes sense. I'm going to take 5 people, and I'm going to line them up at the door out of a group of 20 people in the room. And I'm going to pick only 5. Well, how many people can I pick for the first slot? 20. Well, then that first person is no longer available. So that means I have 1 less person to choose for from this group. And then 1 less for that one. And then 1 less from that one. And so forth. And that's the same thing as that sitting right there. So if I didn't have a calculator, I can do it that way. On the calculator, there is a way to get to it. In the calculator screen right here, push menu. And then you go to probability, number 5. And right there is number 2, which is called permutation. Oh, and there's also another spot for factorial right there. So you can get a factorial right there in the same spot. We'll go down to permutation. In PR, there's a blinking cursor in the parenthesis, and here you need to type in 20. And then you're going to put the comma, which is right down here. Then you're going to put the 5. So there's the 20, there's the 5. And then you hit enter. It's going to give you that number right there, which is the answer. That's the number of ways I can line people up at the door. And the alternate way. So another way to look at it the same way. Okay? If you have ordering, just how many ways can I get the first one? How many ways can I get the second one? And so forth and so on. What if we don't need to count the number of ways to order our objects taken from a group of inset? But we want to know just how many different groups of our objects that can be made. In other words, order does not matter. For example, here's some ways that order does not matter. If you play the lottery, the order in which the numbers are chosen at random does not matter. If you have those numbers, you win. And the way they're chosen is irrelevant. Card games, when you deal out cards, you can rearrange the cards in a certain order to your liking. There's no particular one way to order them. You have the cards, there you go. If I'm going to pick a group for a committee, okay, it doesn't matter the order in which you were chosen, you're there. You're on the team. Okay, choosing teams, same thing. Being the first one chosen or the last one chosen doesn't make a difference. You're all on the team. Okay? That's called a combination of n objects taken r at a time. And that is this formula right here. You'll notice it's a permutation. And then we divide by whatever that r is, the number of items you're taking, that factorial, to eliminate the ordering concept. So that when we have the same list, it doesn't matter the order. We remove the order part. So here's my example. I'm going to show you right here. For an experiment, 4 students are randomly selected from 20. How many different groups of 4 can I make out of 20 students? So this is an NCR. There's my N, and R is 4. So 20, choosing 4 out of the 20. So this will be 20 factorial. This will be 4 factorial. And then 20 minus 4 factorial. Again, we can use our calculator. If you remember that we did this over here. In the calculator portion over here, we can push menu. Number 5 for probability. And combinations are number 3 on our list right here. And you'll see NCR. And you do the same thing. 20, comma, 4. Enter. And there's the number of combinations that we can get. So it is 4,845. Okay? So again, combinations are for when order does not matter. The formula for counting subsets of an inset. In other words, if I have a group of 10 objects or something like that, how many different subgroups can I make? Okay? So how many groups of 1 can I make? How many groups of 2 can I make? How many groups of 3 can I make? And so forth and so on. And there are 2 to the n subsets of a group of n objects. This will include the empty set, so the group that has nobody in it, and then the whole entire group as 1. Okay? So if that made sense to you, if not, here's another way to look at it. If I have let's say 3 objects. I want to know how many subgroups can I make out of 3 objects. Well, I can have a group of nothing, so the empty group. And I can have a group that has, I should say it's 1, 2, and 3. I can have the group that has 1 in it, the group that has 2 in it, the group that has 3 in it. I can have the group that has 1 and 2 in it, 1 and 3, 2 and 3, and then the whole group itself, which is 1, 2, and 3. And so it's 1, 2, 3, 4, 5, 6, 7, 8. And 2 to the 3rd power is 8. That's what they mean by subgroups. Okay? Here's another example right here. And I'm going to move over here and I'll show you how this works. So Luigi sells pizzas, one size pizza, but he claims that he has a selection of toppings that will allow you to have over 4,000 different pizza choices. What is the smallest number of toppings that Luigi can offer? Okay? So what they're saying here is, how many different ways can I do this? Well, I can have a pizza with no toppings on it. I can have a pizza with all the toppings on it, and any subset of toppings all the way through. I can have a 1-topping pizza. I can have a 2-topping pizza, a 3-topping pizza, or however many toppings I have. So that's where this 1 to the n subsets come in. How many different ways can I do this? So I don't know the n number. So but I do know 2 to the n has to be at least 4,000. Okay? So let's find out how many pizza toppings I need to make 4,000. So that's how you would set that up. And since this is an exponential, I need to solve this exponential. The base number is 2. To get to the n up here, I take the log base 2 of both sides. So the log base 2 of 2 to the n, log base 2 of 4,000. So n is going to be this right here. And then I can use my calculator to approximate this out. So we have the log base 2 of 4,000. And I get 11.965, 11.965, which tells me what? Well, I can't have a fraction of a topping. This is what gives me 4,000. He says I can make over 4,000. I need the next number up, which means the smallest number of toppings is 12. He has to offer 12 toppings to hold to his claim. Okay, so there's all the counting principles that we're going to be looking at in this section right here, and some problem types that we're going to be looking at, and we'll take more questions in class.